Good afternoon, students. Good afternoon, students. We will start our today's topic with the wave function, properties of the wave function. In the last class, we just discussed about the wave function. You can remember that we just discussed about the wave function. Wave function is nothing but it is a wave function properties we discussed. So the first important property, nothing but the wave function is a mathematical it's a mathematical representation, right, which gives complete information of the system, which gives complete information of the system or the particle. System, or we just say that is a particle. So this particular part we just studied in the last class. So here we'll just go for properties of the wave function, right. First of all, we discuss the properties and the significance of the wave function. What is the significance, right, of the wave function, and also what is that importance of the wave function we are going to see this class, right. So now the first important property that the wave function is dealing with. So in the last class also we studied about the important postulates, and among that, if this is the case, right, mathematically, if we write like this, right, mod of x psi of x square, if I just write this as a square, then what is actually it means? That it means that it is the probability density of the particle. It is the probability density probability density of the particle. So you already know that we are using probability in quantum mechanics, density of particle, that actually we are dealing with, right. So if this is the important property, one of the property of wave function. Now if this is written, and then we just say that is called probability density. Now in the second case, we just discuss, right, second important property is the second important property is only mod of psi of x. Start with the important second important property. If this is the case is happening, right, second important property that we are going to learn in today's class is here mod of psi square dx, right. So mod of psi of x, right, square. If dx is coming, then this particular is in the form is known as probability of the particle, right. Probability of finding the particle at the probability of the particle which is having a class interval between the class interval between x and x plus d, right. This will be the class interval we are talking about, x and x plus dx, right. Just say that is called x plus. In this particular interval, we'll find that the probability of the particle, right. So that signifies that is the probability of finding the particle. The third important property that we are going to see is right, if this is the case, right, if I just introduce the introduction here with certain limits. Let us consider I am taking the limits as a to b, right. I have taken the interval as x and x plus ds. In the same way, I'm just considering this as psi of x mod square, right, mod square dx. This is the probability. This is what the only we just say that this is the probability mathematically. This is the meaning of the terms whatever we are using. Now this is the case. What is happening in the wave function, we just say that is called the properties of wave function. Now fourth, as we go to the fourth important property of the wave function, that is psi of x must be right. So it must be finite. They say that is called psi of x will be finite and it should be continuous, and it should be continuous. Now this particular important property is been given by the wave function. Now we say that is the properties also, and there may be the limitation also, right? And the first order derivative dou psi by dou x should also be derivable, and it should also have a finite value. Now this is the important properties of the wave function. Now when we go to the significance, right, the important significance of the wave function. So what is actually the importance or the significance of the wave function? Just go in that particular area. So it relates actually when we go for a significance, it is relating. It relates, right? Wave function relates the particle nature, particle and right, particle and wave nature statistically, and wave nature statistically, right? We just say that it's called the statistically. This was the significance of the wave function. We say this is the, so the wave, by using the wave function, we can correlate the particle and wave nature statistically. Now this is important one that we need to understand. The second important significance, what the wave function says, that that it is actually a complex quantity, right? And we cannot exactly measure it, right? So it is a complex quantity, cannot measure. It is a complex quantity, so directly we cannot measure, accurately we cannot measure it, so we cannot measure it. So see, you can by this particular aspect you can just have the information, right? This is a probability. Why we are using probability? So it is a complex quantity, we cannot measure it, right? So that is the reason that we are using probability here. So here I think that we started with the probability concept, the properties of wave function, and then we gone for the significance of the wave function. So now we just deal with the right. Now we deal with the yeah. We just start this. Okay. Now, okay. Now, okay. So right. Now we just start our next important thing is the Schrodinger equation, right? Schrodinger is the name of the scientist who has given us the information regarding the total energy of the system or a particle. So Schrodinger equation, which gives us the information, mathematical information regarding the energy of the system. So there are two types of Schrodinger equations, that is Schrodinger time dependent equation. The short these I'm writing the short forms, so you can just make a note of it. It is actually Schrodinger independent equation. So now the first aspect that we are going to deal here is the Schrodinger time dependent equation, right? Schrodinger time dependent equation. Dependent, right? Schrodinger time, again I write time dependent equation. So how we are going to derive this, right? Schrodinger, for which see in quantum mechanics several people got Nobel Prize. Schrodinger also got Nobel Prize by of mathematical representation of this energy of this system. He has given the mathematical form to calculate the energy of the system, right? So now we just start our today's topic with the Schrodinger time dependent equation. So why we are studying about Schrodinger equations? The Schrodinger equations will give us the information regarding the exact energy of the particle, right? So what we have to do, see, what we have to start with the consideration part, right? Let us consider the particle, right? So we just start with this solution of the Schrodinger time dependent equation first. So for that, let us consider let us consider the particle, right? Let us consider the particle having 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 mass small m, right? And the last class we have seen, and let the kinetic energy and let the kinetic energy kinetic energy let the kinetic energy is square by 2m. Now this particular aspect I already we have already seen in the last class. So we just you already know that kinetic energy is nothing but it is given as half mv square. We are having this idea, right? What we are doing here is that multiplying with m and dividing by m. So what you will obtain here? So the same way, half, you multiply this and you will obtain this, right? Half m square, right, by m. So you already had the information that P is equal to mv. Squaring on both sides, P square is nothing but m square, right? This is what V square. So what I can write now, the kinetic energy, right? So is equal to P square by 2. So let the kinetic energy is P square by 2m, and the potential energy is P. So we just start with our again I am repeating the same thing. Let us consider the particle having mass m, and let the kinetic energy is given by P square by 2m, and the potential energy is given by V. Now you already know the kinetic energy basic equation, half mv square. So we just multiplied and divide by m. So you will get half 1 by m square v square by 2m. That is nothing but P square is equal to m square v square. So the kinetic energy is equal to P square by 2m. Now this was the equation related to the previous knowledge. Now what we are doing again here, what we'll do is that we just derive this values by considering the operators. You are having the information regarding the operators, right? Now, so you are having the information regarding the operator, right? So here also we just start our derivation, right, with the energy operator. You already know in the last class we had the energy operator, which is given by I h bar dou by, right, dou by dou t. This is the information that we are having from our last class, right? This is the energy operator. Again I am reminding that operators are the measuring devices which for the given quantity in quantum mechanics, and momentum operator is given by equal to, right, h bar by I to delta p. So if I write that as p square, we are using p square here, right? So h bar square, del square, and p square. So divided by I square. So you already know that what is I square? I square is minus 1. Here everybody. So what I will write here? So here p square is equal to minus h bar square del square, right? Now one can know that this is what I am talking about, energy operator. This is what energy operator, and this is what is actually del, complete del, right? You can remember this, right? This is del. So this is what momentum operator. You You have to remember this momentum operator. For quantum mechanics, we'll use the operator. So what is operator? Operator is a measuring device of the quantity. So if it is the energy, it is a measuring device. This I h bar dou by dou t is the measuring device for the energy. And for momentum, minus h bar square del square v square. And what is h bar? You already had the information. H bar is nothing but h by 2 pi, where h is the Planck constant. Clear, everybody? Now, we just move forward. What is the total energy? Total energy of the system or the particle is given by, right? What is the total energy? E equal to kinetic energy plus potential, right? This is what we know, right? So E, right, is equal to, what is kinetic energy? P square, you already know, right? P square by 2m, right? Potential energy is what? P. So multiplying psi on both sides, right? Clear, everybody? Let us multiplying the psi on both sides. So what we will get? E psi is equal to square by 2m plus v, right? This will come in the bracket. So into psi, right? Now you already had the information. E is what? You can just see this. E is what? Momentum operator, energy operator. That energy operator is, right? We can have I h bar, instead of that, what I can write? Dou psi by dou t equal to, what is momentum operator? Minus h bar square del square, right, by 2m plus v to psi. Now this is what we got the equation of what you can say, the Schrodinger equation. So this is Schrodinger time dependent equation. This is called Schrodinger time dependent. So we can just write this as this equation actually is known as Schrodinger time dependent equation. STD, Schrodinger time dependent equation. Now, so what we can do is that we just again the Schrodinger time independent equation, where we just remove this particular term. So this is the way how we will derive the Schrodinger time dependent equation. The Schrodinger time dependent equation can also be written as, this can also be written as psi equal to h psi. You can just remember this h is nothing but, here h is nothing but minus, this is completely h. The h is nothing but minus h bar square del square p square by 2m plus, and just remember this, right? So minus h bar square del square by, now this is the Schrodinger equation. See, one thing that you need to remember, that the first part that we see, v here, just write, don't write this v. P is actually only minus h bar square del square. Now this particular term we can just start it with this term. So this term will just right. This is actually not there, right? So it's only minus E is equal to h bar by del, right? Now this is what momentum operator is all about. So we just write this is right. This is not there. So okay, right? So minus h bar square. So what is that? P is equal to h bar by I del. So we just write minus h bar square del square. So total energy of the system. See, we just started with energy operator. Again, I'm repeating the same thing. I h bar dou by dou t. This is the energy operator. Operators in quantum mechanics are used as measuring devices. So the momentum is given by h bar by I del, right? So del is a operator, right? So P square is equal to h bar square del square by I square. So I square value is minus 1. So P square is equal to minus h bar square del square, right? So the total energy of the system is given by E is equal to kinetic energy plus potential energy. What is kinetic energy? P square by 2m, just now we have derived, plus V. So just multiplying psi on both sides, so we'll get E psi is equal to P square by 2m plus V into psi. So I h bar dou psi by dou t is equal to minus h bar square del square by 2m plus v into psi. Now this is the Schrodinger time independent equation. Or else we can just write this as E psi is equal to H psi, where H is nothing but minus H bar square del square by 2m plus V. Now this is what actually we obtain as the Schrodinger time dependent equation. So in the next class we'll just see Schrodinger time independent equation, right? So we'll just see again one thing you need to remember, right? So if you just do the practice, then definitely you can move to the, you can understand more things, right? So it is completely, it depends upon your practice, right? And the concept of quantum mechanics, if you can just remember, so that concept of quantum mechanics will yield you to understand so many things for practical application. And here we'll also discuss in the class, in the later section of the classes, that actually we are moving towards the application. See, after studying this quantum mechanics, we will have we have to see that there is an existence of what is the importance of quantum mechanics to a civil engineering student or civil engineering and computer science engineering student. So for that instant, we'll just see that part also in the later part of our syllabus. So the applications of the what you can say, the important applications for computers, right? Particularly we'll deal with the computers also, which is used for each and everybody. So now we'll move to the next one, that is Schrodinger time independent equation. First we'll derive this, right? Schrodinger. Now Schrodinger time independent equation, right? What we'll do is Schrodinger time dependent. Just start this equation, right? Time independent. For this also we need to consider the particle. See, basic things are there which you have studied in the intermediate, and if you have not remember also, there is no problem. So what we are doing, see, you can just, anyone can easily remember this, right? Let us consider the particle. Let us consider the particle, right, of mass m moving with the velocity v. Let us consider the particle of mass m which is moving with velocity this I think that everyone can remember. Mass is what? Consider the particle having mass small m, right? So which is moving with the velocity. See, again I'm repeating the same. See, I'm going very slow. Why? Because you can just easily understand this topic now. So let psi be the wave function let psi be the wave function along the wave function at a wave function of the particle, right? Let psi be the wave function of a particle right, along x comma y comma z, right? X comma y comma z direction. So I think that this is the very what you can say, easily you can just remember this. So x comma y comma z directions. Now you already know that the de Broglie wavelength, right? The de Broglie so the de Broglie, again I'm right here. I'll try to write this the Broglie wavelength. So the de Broglie wavelength wavelength, that is given as lambda is equal to h by m, right? And also it can be written as h by p, equation number 1. So we have considered the particle which is having mass m moving with the velocity, right, v, and let psi be the wave function, let psi be the wave function of the particle along the x comma y comma z direction, and the de Broglie wavelength of the particle is given by lambda is equal to h by mv, and h, that is, it can also be written as h by p. Now what we do is with this, right, so we just use our basic classical wave equation. Since the particle is behaving as a wave, the classical differential wave equation, the classical differential wave equation we are having, right, with wave velocity v, with the velocity v, right, with the velocity. So what is that classical wave equation of the velocity v? Just see, given by velocity v given by dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square is equal to 1 by